Let's start now, and it's my pleasure to introduce our speaker of today, Guilhem Mureau from University of Bordeaux, who will be telling us about his recent Eurocrypt result on cryptanalysis of rank 2 module LAP in totally real number fields. So Guilhem, you can start whenever you want.
Yep. So thank you, Elena, for the introduction. Thank you very much for your invitation. So actually, this is my first paper and first talk, so I'm really happy to participate. I will present you results done with Alice Pellemari, my PhD director, Georges Piastock, and Alexandre Wallet. So we give an algorithm to solve a problem called module leap. So actually, LEAP stands for lattice isomorphism problem. So we solve it in some particular cases. So actually, LEAP is quite an old problem for mathematicians, but it's really recent in cryptography. The first apparition of LEAP in crypto was in 2022. And for us, the starting point was a paper from Ducasse, Postlethwaite, Poole, and Van Voorden, also in 2022, in which they introduce a signature scheme, Oak. So it was submitted to the NIST for the additional call for signatures. And it is based on a module leap problem. So actually, the problem is defined in the paper of Oak. So it uses a module leap over cyclotomic fields, and it's really efficient and compact. It takes advantage of the module lattices, which are compact ways to represent high-dimensional lattices. So in this talk, I will present an algorithm for solving rank 2 module leap. So module leap for rank 2 lattices, and in a special case of totally real number fields. It is polynomial in many times, but I should emphasize that this doesn't break Hawk, because Hawk actually uses cyclotomic fields. Cyclotomic fields are totally complex fields, which is quite the opposite of totally real. So the attack, the algorithm I will show you doesn't apply in this case. So here's the plan. I will first give all the background on lattices and define the lattice isomorphism problem, and do also the state of the art for the problem. Then I will define the algebraic variant, so module leap. The third part is the main contribution, so the algorithm for solving the problem. And the main point in the algorithm is to interpret the problem as solving norm equations, which is a classical problem. So I will present you more in details how we can do that in the fourth part. And finally, some results. So let's get started. Let me fix a positive integer n. What I call a lattice in Rn is a set of integral combinations of linearly independent vectors. The data of the vectors, so the concatenation of the BIs, is an invertible matrix with real coefficients, and it's called basis of the lattice. So in practice, we always represent a lattice by one of its bases. And of course, the basis is not unique. B prime, an invertible matrix with real coefficients, is also basis of the lattice generated by B if and only if there exists a unimodular matrix, so an invertible matrix with integer coefficients, such that B prime is equal to BU. We say that two lattices given by basis B and B prime are isomorphic if there exists an orthogonal map which maps L on L prime. So here is an example in dimension 2, for example. So on the left-hand side, you have a lattice represented by basis B1, B2 in red. So let's say you take a rotation, you take an orthogonal transformation of the space, so you rotate the lattice. Then what you get is the rotated lattice, and in general, you don't know the image of the basis, but you know another basis of the rotated lattice, so say B prime, given by B1 prime and B2 prime. And we get a relation between B and B prime, since OB is the basis of L prime by the previous characterization. There exists a unimodular matrix such that B prime is equal to OBU. And the lattice isomorphism problem is precisely given the isomorphic lattice, basis of the isomorphic lattice B prime to recover O or U such that the relation is verified. Of course, you can recover either O or U since you know also B and prime. So it's enough to get one. So a possible reformulation of the lattice isomorphism problem is using quadratic forms to a basis B. We can associate its Gram matrix. So it's the symmetric definite positive quadratic forms given by B transpose times B. We say that two Gram matrices are congruent if there exists a unimodular transformation U, such that G prime is equal to U transpose times G times U. And we have the following facts. So two lattices represented by B and B prime are isomorphic if and only if their Gram matrices are congruent. The proof of this fact is really simple. We can check it. So suppose that we have isomorphic lattices. So we have a relation B prime equals OBU as before. And then we can just compute the Gram matrix associated to B prime and check that it is congruent to the one of B. So conversely, if we suppose that we have a congruence relation between the two Gram matrices, an easy computation shows that B primes times the inverse matrix BU is an orthogonal matrix. So we can use it to reformulate LEAP with Gram matrices. Given Gram matrix G and G prime congruent to G, the problem can be to reformulate to find U unimodular satisfying the congruence relation. The two problems are equivalent. This is due to Cholesky decomposition, which essentially says that given a Gram matrix, you can recover factorization B transpose B, so you can recover the basis of a lattice with Gram matrix G. And in practice, we work with rational basis and rational Gram matrix, and we want to keep manipulating rational numbers. So we want to avoid manipulating the orthogonal map, which doesn't often have rational coefficients. So we prefer the quadratic form, which somehow forgets about the rotation. How can we solve LEAP? Well, the first step, so actually there are two algorithms for doing that, and the first step is common. So first you have to compute many short vectors in the two lattices. That is, you must solve the SVP, shortest vector problem, which is well known to be a hard problem in lattice-based cryptography. And then you will try to match these vectors to reconstruct isometries, because you know that an isometry preserves the norm. So given two vectors of the same length in both lattices, you will try to map them. It will give equations, and you can reconstruct the isometry this way. So this allows you to compute all isometries. And for example, there is an algorithm of Plesken and Souvigné doing that. and also an algorithm by Avif and Regef, which has complexity n to the big O of n, where n is the dimension of the lattice. This is essentially due to the fact that solving SVP is already exponential time has exponential time complexity. Okay, so now let's move on to the algebraic variant. This time I fix a power of 2 integer n, and we will work with the cyclotomic field generated by a 2nth primitive root. Its ring of integers is generated by zeta, the root of unity. And there is a canonical map from L to R to the n, which can be either the canonical coefficients, if you prefer, or the Minkowski embedding. The cyclotomic field contains a subfield K, so it is generated by zeta plus zeta minus 1. It is called the maximal totally real subfield of L. So it is an example of totally real fields. And in fact, you have to keep in mind for the following that the algorithm, our attack works on this subfield and not on the cyclotomic field. Okay, so in module leap, we work with modules, module lattices. An example of a module lattice is, for example, an ideal or fractional ideal. So it is a rank 1 module lattice. But if you want something with rank strictly bigger than 1, I think the easiest example is OL plus OL. So you take two copies of the ring of integers, and this is a module lattice. That means it has a OL module structure. In this case, it is free. It has a basis. This is something really particular for module lattices. In general, we don't have basis. We have to work with something called pseudo basis. But okay, in this case, we have basis. And if we take its image by sigma L, the embedding to R to the n, we take the image coordinate-wise, then we get a standard lattice, a Euclidean lattice in R to the n. So actually, OL plus OL is the module lattice used in Hawk. And as I told you, our attack will work over the subfield. So for example, for the module lattice OK plus OK, 2 copies of OK. I will define module leap as in Hawk's paper. So it will be in terms of quadratic forms. We need to get something similar to quadratic form in this case. So to basis U of OL plus OL, it is just an invertible matrix with coefficient in OL. I can associate the equivalent of its Gram matrix. It is also called a Humbert form. So it is given by U star times U. The star here is for transpose and conjugate. So you transpose the matrix and take the conjugate of all elements. It is something symmetric definite positive, Hermitian definite positive. And if you make appear the identity between the two U, you get what looks like a congruence relation between G and the identity. Identity that you can see as a Gram matrix. So the Gram matrix associated to the identity basis. And module leap is defined this way. So given as input a Gram matrix G congruent to the identity, the problem will be to compute all basis U such that G is equal to U star times U. So we are really copying the problem module leap for unstructured lattices. This is really natural. So the link with Hawk, the signature scheme is as follows. In Hawk, so it is a signature scheme. I will not get into details on how it works. But in Hawk, you have two keys, a basis of the module lattice OL plus OL, U, which is secret. And the public key is the gram matrix associated. So if you want to recover the secret key from the public one, it is exactly what we define to be a module leap problem. And actually, any solution, this is quite remarkable, but any solution to this problem, any matrix V invertible with coefficient in OL, such that B star V is equal to G, is a key recovering. This is really strong, but you get the key up to isomorphism. So how can we solve it? You can apply the embedding into Rn. So you will get a lattice, a Euclidean lattice, and you can solve the problem with the embedded lattices with the algorithms we saw for the unstructured problem. But you have to be careful because the solution you will get will not always be solution for the module leap problem. This is because in module leap, we are looking for solutions which also must preserve the algebraic structure. So in some sense, module leap is leap restricted to module lattices, and the solutions we are looking for must preserve the structure. And the Pleskin-Sauvigny algorithm we saw can be adapted to this case. So that means you can adapt Pleskin-Sauvigny algorithm to look for isometries which preserve the algebraic structure. But it still needs to enumerate short vectors, so this is still a very hard problem. And the question we asked is the following: can we solve module leap more efficiently and using the algebraic structure? So now I will present the algorithm for the example of the module lattice in the subfield. So we'll focus on OK plus OK. So here is what happens. So let's suppose that U is a basis of OK plus OK. Okay, we know its gram matrix. It is public, and it has this shape. But since K is a totally real field, the conjugate, the bar, I can remove them. A bar is just A. So I get for the first coefficient A squared plus B squared. And same thing for the last one. In particular, the fundamental observation, which is easy, but it is that diagonal elements of the gram matrix are sums of two squares in OK. And sum of two squares, we can reinterpret it as relative norm equations. This is because A squared plus B squared can be written A plus IB times A minus IB. And this is the expression of the relative norm of the element A plus IB, which lives in the cyclotomic field, so in the quadratic extension above L. So for example, the easiest example is when K is equal to Q, and L is Q of I, rational Gaussian elements. You can write, for example, 5 as 1 squared plus 2 squared, and this is the norm of the element 1 plus 2i. So this is a relative norm equation in Q of I. And the main idea for the algorithm is to solve norm equations. It will allow to reconstruct the secrets. We need to do stronger than just solving norm equations. We need, in fact, all solutions. For example, if we solve the norm equation for the first coefficient, if we get all the solution, among the solution we must have A plus IB, which will give the first column of the secret key. So we really need all of them, and this is something new. So it is based on an algorithm from Guilhem and Sidlow. So it works as follows. So given as input an element Q, we want to write as a sum of two squares, and the prime factorization of its absolute norm. The algorithm will output all elements x and y in OK, such that Q is the sum x squared plus y squared. And it runs in time polynomial in the degree d of the field and the logarithm of the norm to the r, where r is the number of distinct prime factors of the ideal generated by Q. So let me recall that for ideals in OK, we have a unique prime factorization. So that means that Q OK, the principal ideal generated by OK, can be expressed uniquely as a product of prime ideals, and the number of distinct prime ideals appearing in the factorization, what I call R, is really an important parameter for the complexity of the algorithm. And in particular, and this is also surprising, the running time bounds the number of solutions. There are not too many solutions. But we get a problem. R in general, in average, is not too big, but it could be in the worst case, and we don't want this to happen. So the solution is to do rejection sampling. So we use a standard fact that we can sample Gaussian elements in the module OK plus OK. So that means that given G, the Gram matrix, we are able to sample module vectors UV following a discrete Gaussian distribution. And if we make two calls to this algorithm, so we sample two module vectors, we call V the concatenation of the two columns, and suppose that this matrix is actually invertible. What we can do is we conjugate the Gram matrix, so we compute a new one, V transpose times G times V, and we hope that the new diagonal coefficients don't have too much prime factors. So we need now we need an assumption to make sure that it happens with a good probability. And this is what we formulate. So it is based on theoretical results and also experiments. What we assume is that so given an element Q, which can be written as the norm U squared plus V squared of a module vector, then the probability that the principal ideal generated by Q is prime is bigger than 1 over rho k, so the residue of the Dedekind zeta function at 1, times log s times p of d, where p is an absolute polynomial. And for our experiments, so for maximal totally real subfields of power of 2 cyclotomic fields, what we got is that rho of k is very small, and p has degree 1. Okay, so now we get everything to build the algorithm. So given as inputs a Gram matrix, we will compute all the solutions. U transpose U is equal to G. So first of all, we initiate two vectors to be 0, and we do the rejection sampling. We randomize the input until the diagonal elements are generate prime ideals. And once we get that, we can call our norm equation solver. In input of the algorithm norm equation for writing elements as sum of two squares, in input we need, of course, the element we want to write as sum of two squares, and also the prime factorization of its algebraic norm. So in general, it could be costly to compute the prime factorization, but in our case, we built Q1 and Q2 such that they generate prime ideals. And to test if an ideal is prime, the first thing is to compute its algebraic norm and factor it. When we call the two norm equation algorithm, at this step, we know the prime factorization of the elements Q1 and Q2. So this is free at this step. And finally, we will return this set of matrices. So on the left, ST S prime T prime is a matrix such that its gram matrix associated will be a solution to module leap with G indexed V. The gram matrix we obtain after randomization. So to get a solution to the initial problem, we have to divide on the right by D. Okay, so let me do a little example on Z. So of course this is quite trivial, and we could do it by hand, but just to make sure that you get how the algorithm works. So we consider this gram matrix, and we want to compute all invertible matrices with integer coefficients, which have this gram matrix. So for the diagonal coefficients, the first one is prime, but not the second one. So we will do the randomization step and suppose that we pick these two vectors with Gaussian gram. We compute the new gram matrix. And this is exactly as we want. We get prime coefficient on the diagonal. Okay, so then we call the norm equation solver. So let me just do an example. I won't list all solutions, but for example, you can write 2 as the norm of 1 minus I and 5 as the norm of negative 2 plus I. So the matrix you get is in the column 1 and minus 2 and minus 1, 1. And you divide on the right by D, the coefficient obtained during the randomization. And you check that this matrix is a solution to the initial problem. Okay, so the complexity of the algorithm is the following. We can, and under the randomization assumption, it will solve module leap in expected time polynomial in rho k, d, the degree of the field, and the size of the coefficient, the size of the matrix. And actually, for the experiments we did, rho k was very small, so we can get rid of it. But we can prove it, actually, that it is always small. So that was for the case of the module lattice OK plus OK. But in fact, in our paper, we did it for every module lattice of rank 2 over any totally real number field. And in fact, you can define module leap for any module lattice over any field in terms of gram matrices or pseudo gram matrices, because you can't work with, you have to work with pseudo elements. So if you know, but the problem is really similar. You have to find, you look for matrices U such that G prime is equal to U star times G times U, and U must also satisfy some conditions. Okay, so the full attack, the full algorithm actually solves module leap for any rank 2 module lattice over any totally real number field. But there is an extra difficulty because during the randomization step, in general, you can't hope for having Q1 and Q2 prime ideals. This is because these elements belong to your module lattice. I'm sorry. These elements are norms of vectors of your module lattice. So in particular, they all lie in a common ideal, which is the ideal generated by the norm of the vectors of your module. And if this ideal is not trivial, you get, in general, you don't have any chance to get prime ideals during the randomization. So this is actually what the full statements look like for any module lattice. So it solved the problem in complexity in time polynomial in row K, log of the discriminant of the field, the size of the input, and all of this to the exponent r plus 1, where r is the number of distinct prime factors of g of m. So this tells you that the complexity is really linked to this gram ideal. This is an invariant of the module. If the gram ideal has too many factors, you can do better. Okay, so now I will focus a little bit on how we can solve norm equations. So I will get into details of the norm equation algorithm. So let me recall what we want to do. We have Q, an element of OK, and we want to find all the elements A and B such that Q is the norm of A plus IB. So the strategy is as follows. First, we look for the ideals in OL, the quadratic extension, which have relative norm QOK, what we want. And then on each of these ideals, we will check if they are principal and try to extract a generator with the good norm. So actually, this is quite difficult to check if an ideal is principal, but we are in a particular case where we can apply an algorithm by Gentry and Sidlow, which is polynomial time, and we'll do at the same time, so checking for principality and computing a generator with the good norm. This is really what makes the attack efficient. So for the first step, for computing the ideals above with the good norm, this is as follows. Because we have a quadratic extension, we have 3 cases for the ramification. So first, let me suppose that QOK is a prime power ideal. We want to understand who can be the prime ideals in OL with norm QOK. We have to understand the behavior of P seen as an ideal of OL, the ideal generated by P in OL. And there are 3 cases. It can be either a prime, again, a prime ideal Q. It can ramify to be, that means it is the square of a prime ideal, or it can split. That is, it is the product of 2 prime ideals. And this is the most common case. So in the first case, when P is inert, we have only one possibility for picking an ideal with norm QOK. The only candidate is Q to the E over 2. Same thing when P ramifies, we have only one candidate. But when it splits, so we have to take for G a product of some power of Q1 times some power of Q2. And we have a degree of liberty when choosing the exponents. And this gives E plus 1 candidates. And in general, for Q products of prime Pi to the EI, the number of candidates G will be log of the norm to the R, where R is the number of distinct prime factors. And for the second step, as I told you, we use an algorithm by Gentry and Sidlow, which, as input, you give it a basis of an ideal, J, and an element Q, which is, you have to think about it as the norm of the generator you are looking for. And the algorithm will return either fail if the ideal is not principal or doesn't have a generator with the good norm. And if it does, it will compute such a generator. Okay, so we have everything to give the norm equation solver. So let me recall that in input, we need the prime factorization of the absolute norm of Q. The first step is to compute the prime factorization of QOK, which is an easy step because factoring the ideal generated by Q is almost the same thing as factoring the norm. So this is almost an input of the algorithm. So first step is easy. And then we compute all the ideals in OL with the good relative norm, as we saw before. And for each of one, we applied the Gentry-Sidlow algorithm with input J and Q, the relative norm elements. And if it returns an element G, then we know that G is a solution to the norm equation. We will add it to a set, but we will also add all its multiple by roots of unity, since they are also solutions to the norm equation. And finally, we will return only the elements of S, which are also in OK plus I times OK, because we are interested in finding elements A and B in OK squared. We want only the coordinates in OK. Okay, so I have some time to get into details of the Gentry-Sidlow algorithm. I will present it for the cyclotomic field for power of two cyclotomic fields. So we did an implementation of the Gentry-Sidlow algorithm for any cyclotomic field, but just for this is an easier case. So as input, it takes a basis of the principal ideal G times OL and the relative norm of the generators, and it will output G up to a root of unity. So the principle is quite intricate. The first step is to pick a prime, rational prime, which is congruent to 1 mod to M. And the idea is to compute a big power of the ideal. We will compute GOK to the P minus 1. And this is possible doing a binary exponentiation and using the knowledge of the norm GG bar to avoid coefficient blow-up. So we can compute this big power efficiently. and if we take an LLL reduced basis of this big power, the first basis vector will have shape, so generator to the p-1 times v, with v a short vector. By Fermat-Littl's theorem, you know that g to the p-1 is equal to 1 mod p. And so if p is big enough, you will get v, taking the first vector mod p. And so you know exactly g to the p-1. Next, you want to reduce the exponent in the power of g. So you can do it like this. You take another prime with the same conditions, and such that it's GCD with p-1. The GCD of p-1 and p'-1 is equal to m. In the same way, you will be able to compute g to the p'-1 mod q for any q. And using a Bezout relation, you will get g to the m mod q for any q. So if q is big enough, you will get g to the m exactly. And since m is not too big, you are able to extract m float. And so you get g up to a root of unity. So here are the experiments for the full attack, the full algorithm. The first table is for subfields of power of 2 cyclotomic fields. So we did a full implementation. It is available on our Git, as well as the Gentry algorithm. Okay, so just to conclude and also to give some perspectives, over the cyclotomic field, the Gram matrix has this shape. And we say that if the field is totally real, we can get rid of the conjugate and we have sum of two squares. But over the cyclotomic field, this is not true. You can't get rid of the conjugates. But we can still say something. Writing the elements A and B in a basis of K. So A is A1 plus A2, same thing for B. We see that the first coefficient, A bar plus B bar, is the sum of 4 squares in OK. And sum of 4 squares, you can interpret it as a normal equation in quaternary algebra. So this is actually what we are trying to do. Doing the same idea of solving norm equation, but this time is in quaternary algebra, and things get more intricate when you get into non-commutative algebra. Thank you very much for your attention.
Thank you very much, Guillaume, for the nice talk. I am asking if there is any question. If you have a question, you should be able to type it in Q&A, and I will be able to read it in case you don't have an option to speak. While I'm waiting for the questions to arrive, I have several questions on my side. So you implemented Gentry-Gidlow, and actually we also at some point tried to do it. Did you implement it in Sage or in ParisGP? We used it with my student, and the memory was a bit of an issue there.
Oh yeah, so actually it is implemented in Sage, but calling function in Paris. But depending on the version of Paris you have, we included a parameter to either call Paris for doing the LLL reduction. I think it's called Flatter. The newest version of LLL is called Flatter in Paris. Yeah. And if you don't have it, you can do it using the classical function, but it's slower. So this is why you get problems of memory, I think.
I see. Yeah, I guess that's the case. I have another question. If you go to to slide 26 when you were describing an algorithm for well, I don't remember exactly the name, for solving the norm equations. I think it's 26. Yeah. So you say that you know factorization of the norm. How do you know it?
This is an input of the problem. And for us, this is not a big deal because at the end of the randomization, we know that Q1, so for example, the first coefficient of the Gram matrix, generate a prime ideal, and checking if it's generate a prime ideal, the first step is to compute the factorization of its algebraic norm. So yeah, so at the end of the randomization, you know the factorization of the elements you want to write as a sum of two squares.
Okay, so but then so it practically you know the factorization because you built it from small factors. It won't be a big issue to factor it, to factor those that you sort of you at some
yeah,
point
well,
you
actually the factorization of these elements is computed during the randomization. When you check if it generates a prime ideal, you have to compute the factorization of the norm. Oh no, I'm sorry. You don't want to. No, you don't want to compute it, but you want to check if it is a prime power.
Yeah, so that's simpler.
Yeah,
That's
of course.
definitely simpler.
Yeah. If it's not
Okay.
a prime power, you know that you don't have a prime ideal.
Okay.
Yeah, of course you don't want to factor. Yeah.
Yeah, and also when we were looking at with my student and at this gentry at the algorithm for solving PIP, a principal ideal problem, it wasn't really obvious to us when the algorithm does not receive on input the prime ideal, principal ideal, that it outputs. So if it's not principal, it's unclear what it outputs.
If it's not principal, it should fail at some point when you try to extract a root. I think this is the step where it fails. But it does all the LLL reduction, and this is really costly. So you know almost at the end that your ideal was not a principal.
Yeah. Okay. That's nice. Thank you very much. I have one more question, maybe more general. I think in practice, when you look at Hawk, they actually don't. I have the impression that you don't really need to find like really shortest vectors. Is this true that you can just make it, or you can find the isometries using approximate shortest vector, or you really have to have?
No, I think you don't have to solve SVP in its exact form with an approximate coefficient. It should be enough, but you want to have I don't know. So if you want to have a luck to get two vectors with the same length, of course you don't have to take the approximate factor to be. But it's not sure. No, you don't have to solve zip exactly. No.
Yeah. Okay. There is a question from Gora. He's asking, what do you think about the future of Hawk then, given your tag?
So thank you, Gora. There is a big step from totally real fields to cyclotomic fields, I think. This is really much harder for cyclotomic fields. What we try to do with quaternion algebra is much more complicated. And actually, we are able to prove, we are writing it right now, we are able to prove that module leap over cyclotomic field is equivalent to an instance of the principal ideal problem in some quaternion algebra. This would allow the key recovering. and we don't really understand the complexity of PEEP in quaternion algebra, but we think it's still a very hard problem. So Oak is not broken for the moment.
It also should be hard quantumly because it's not commutative, right? Because PEEP quantumly is polytime if you don't in commutative
but for
structure.
number fields, PEEP for quaternion algebra, I don't know. There is another question.
Yeah, there is another question from Alexander Karenin. Theoretically, one could construct a mod lib problem with a non-identity gram matrix as an input. Can this algorithm be adapted to such setting?
Yep, so thank you for the question. Exactly, and this is what we did in our paper. We gave a general definition of module lib with non-identity gram matrices, and this is what we solved. We solved the problem in this case, but still for totally real number fields. Yeah.
Yeah. Okay. I don't see any further questions. I think at this point we can thank the speaker. Thank you very much, Guillaume.
Thank you again.
It was really nice. It was really nice to hear you, and I hope we see each other at Eurocrypt.
Sure. Yeah.
Thank you very much. Thank you everyone for coming.
Thank you.
Thank you. Bye-bye.
Goodbye.